In 2.2, we introduced the concept of subsets. In 2.3, we follow that up by emphasizing some more set operations, specifically with two sets. Now, we aren't going to do much bigger than 3, but in 2.3, we start talking about unions and intersections and subsets in more detail. Now, within my universal set U, there are 4 different cases that can exist when you have 2 sets represented. My rectangle represents the universal set, so I'm going to label each of my rectangles as U for the universal set. Case 1 is when we have 2 sets that are disjoint, when they don't share any elements. So disjoint sets would look like 2 circles that do not touch. So set A and set B are separate from each other, although they're both part of the universal set. Go to my Kroger example. If Kroger is my universal set, set A might be the items in the freezer section. Set B might be the items in housewares. They are not the same set of items, but they both exist within the universal set. Case 2 would be the situation that exists when you have a subset. So you have a subset relationship. For example, with this drawing, I would say that B is a subset of A because all of loop B is contained within loop A. Case 3, we would say are equal sets. If we have equal sets, they share all of the same elements. So even though I have 2 different sets, I really only need 1 loop to represent them. And we don't draw this Venn diagram very often. Case 4 is one we're going to see a lot, where we have overlapping sets so that there is an intersection between the 2 sets. So when we have overlapping sets A and B, they share some elements, but at least one of them has elements that are not in the other. Another term that you need to be familiar with when we're talking about our set and subset relationships is complement. A complement, which it looks like A prime, A complement is the set of all elements that are in the universal set but not in A. So A complement, A prime, another way to say that would be to say not A. When I'm talking about the complement of A, I'm talking about not A. So let's go ahead and draw our overlapping Venn diagram with 2 sets so that we have set A and we have set B. And then I'm going to shade what is not A prime. So this is my A loop. I won't shade anything inside that loop, but I'm going to shade everything else. So anything that's out there floating around in the universal set, anything that is in the B that is other from A, all of this that's shaded is not A. Now, if I consider A, so everything inside the A loop, together with, if I add to that everything outside the A loop, A plus not A, I have everything in the universal set. So A and its complement together include the universal set. A way to put that in set builder notation is to say that not A, or A complement, is the set of all elements X such that X is an element of the universal set and X is not an element of A. So A prime or A complement are all the elements in the universal set that are not in A. And that's not supposed to be a symbol there. I just messed up on my fancy brace. So set builder notation, that is how you would designate or denote A prime. Let's look at the next page and talk again about intersection and union. We've already addressed and introduced intersection and union. We're going to go over them again. Intersection, remember, think about the intersection in the road. If you're part of the intersection, you are part of both sets. So there's my symbol, A intersects B. The key word for intersection is and. So I'm interested in what is in both A and B, what they have in common. So if I look at my universal set and I've got overlapping sets A, B, and I shade the intersection, I'm shading this region that is part of both the A and the B loop. So A intersect B in set builder notation represents all the elements X such that X is an element of A and X is an element of B. So to be in the intersection, it has to be in both sets A and B at the same time. Then we have union. Union, my keyword, is OR, and it's the set, the elements of the set that are in either one. There's my OR. But now remember, it's the inclusive OR, so it could be in both. That's fine. But we're really interested in anything that's in A as well as anything that's in B. So my inclusive OR, A or B or both. Set up our universal set with our overlapping loops, A, B. If I'm going to shade the union, I'm going to shade all of loop A as well as all of loop B. So A union B, A or B, is the set of all elements X such that X is an element of A or X is an element of B. So I shaded 3 regions: the region that is just A, the region that is both A and B, and the region that is just B. Now there's an activity here that we typically do in class that helps us to understand the number of elements in A or B. I'm going to go ahead and give you the rule right now. I want you to think about this. If I made set A the set of students wearing glasses, and I made set B the set of students wearing tennis shoes, and I asked everyone who's wearing glasses to stand up, and I counted you. And then I asked everyone who's wearing tennis shoes to stand up, and I counted you. Do you think that somebody might stand up for both sets? Do you think that there are pretty good chances that we have at least one person who wears glasses and has on tennis shoes? Well, probably, right? At least one that would be in this intersection of both sets. We can't count that person more than one time because they only exist once. So when we think about the number of elements in the union, we need to think, you know what? I don't want to count this intersection as part of A and then count it again as part of B. I just want to count it one time. So I need to subtract out what would be repeated. Let's set up an example with some numbers. Let's say we've got our universal set. We've got A, we've got B. We're going to put 5, 3, and 6 here. So if I have the number of elements in A, so my cardinal number for A is going to include both of these regions because that's my A loop. So 5 plus 3 is 8, correct? There's 8 represented in A. Maybe that's 8 people. We've got 5 people who just wear glasses, 6 people who are wearing tennis shoes, and 3 people who have on glasses and tennis shoes. So we have a total of 8 people wearing glasses. How many people do we have wearing tennis shoes? Well, we've got 9. Total of 9 people wearing tennis shoes. But 3 of those people are counted here and here. We don't want to really count them twice. If I look to see how many people are represented in my diagram, I've got 5 plus 3 is 8 plus 6 is 14. But if I add up these two numbers, I get 17. Well, the difference between 14 that's showing here and 17 that's showing here is that we, over here, where we just looked at the cardinal numbers, we counted that 3, that intersection, twice. We don't want to do that. So when we're looking at the number of elements in the union, A or B, we have to remember that we can start with the number of elements in A, and we can add the number of elements in B to that, but then we have to subtract the number in the intersection. We have to subtract the number that show up in the intersection. So for our example that I have given right here, we've got the number of elements in A is 8, the number of elements in B is 9, but we've got to not count this intersection twice. So we have to subtract out that 3. 8 plus 9 is 17, minus 3 is 14. And if I count 5 plus 3 plus 6, that's the 14 that I get. All right, this is the example that I typically do in the classroom. I say, all right, how many students are at least 5'5" and wearing tennis shoes? That's an intersection. That's not the question that I needed to ask on that. That would be asking how many are in the intersection. I would need to know, or wearing tennis shoes. We can't do this because we don't actually have a class, but I'm going to tell you that when I've done this with my class in the past, in one semester, I had 22 students in the classroom. If set A is the number of students who are at least 5'5", I had that semester 9 people who were at least 5'5", and then I had 12 people who were wearing tennis shoes. When I asked them how many were both 5'5" and wearing tennis shoes to get that intersection, A and B, I found out that there were 6 of them that were at least 5'5" and wearing tennis shoes. So how about how many students in the room were 5'5" or wearing tennis shoes? Well, if I look at just the number who were that tall and the number who had on that kind of shoes, it looks like 21 out of my 22 students. But when I take that 21 and I subtract the number that we counted twice, 21 minus 6, so that I have, according to my formula up there, the number in A plus the number in B minus the number in the intersection, I would have 9 plus 12 gives me my 21, minus 6 means that there were just 15 out of my 22 students who actually stood up when I asked them to. Okay, set difference. A minus B is the set of all elements A that are not in B. So if we sketch our overlapping sets, A minus B means I'm starting with A, so I'm interested in the A loop, and then I take out B. So this region that's also in B, I don't include it. I'm interested in just A. I'm interested in just A. So in set builder notation, this looks like A minus B is the set of all elements X such that X is an element of A, and at the same time, X is not an element of B. X is in A, not in B. Another way to look at A minus B is to think of it as A and its intersection of not B. A intersects the complement of B. All right, next page. B minus A. If I'm doing B minus A, where am I starting? Well, I'm starting with the elements in B that are not also in A. So if I have my universal set, AB loops, if I want B minus A, I'm starting with my B loop, but I'm ignoring the things that are also in A. So I am shading just B. B minus A is going to be the set of all elements X such that X is an element of B, X is not an element of A. Or B minus A is where B intersects not A, complement of A. Those are all general examples. Let's do a specific example. Here is an overlapping set A and B. We've got our Venn diagram set up. And we want to list in roster form what elements we have. We're going to start with the elements of the universal set. Now, the universal set is going to include anything in set A or set B or out here in our rectangle. If I ever ask you, when I ask you to sketch a Venn diagram, it needs to be in a box, in a rectangle, so that you have a place for these elements that are in the universal set but not in either one of the specified sets. Let's go least to greatest again to make sure we don't leave anything out. When I count my elements in the universal set, I have 1, 2, 3, 4, 5, 6. So I need to make sure I have all 6 of them listed least to greatest. That comes out to be 2, 4, 5, 6, 7, 8. Now I'm going to look at the A loop. The A loop just includes 2 numbers, 2 and 4. The B loop, roster form, includes 3 different elements, 4, 5, and 7. I do have to include the fancy braces around my roster form or it is not correct. Make sure you include your fancy braces. All right, where A intersects B. A intersects B, that is my keyword, and I want to know what elements are in both A and B. I can get that by looking at my picture or by looking at my lists and comparing the elements in both A and B. In the Venn diagram, I see that 4 is in both of those loops. In my list, I see that 4 is listed as an element in both sets. So the intersection is 4. The union, remember that's my keyword or, means anything that is in A or B or both. So when I'm looking at the Venn diagram, it is anything inside a loop. Well, everything with these two are inside a loop. So those 1, 2, 3, 4 elements are in A or B. If I'm looking at my list, I use every number listed one time. So I have 2, 4, 5, 7 in A or B. Now let's look at the complement and then the difference. Not A, or complement of A, means everything that's not inside the A loop is in the universal set, but not inside the A loop. To figure that out, I'm going to cover up the A loop. So let's see, let me get something to cover up the A loop with. I'm going to cover up set A, and what's left is not in A, the complement of A. So I've got 5, 6, 7, 8 in the complement of A. You can do this by looking at the Venn diagram. You can also do it by looking at the list. If I look at the universal set, compare it to set A, I take those elements out, and what's left is not A. Then I've got not B, or the complement of B. So this time I'm going to cover up the elements in the B loop. Everything outside of that B loop is in not B. So 2, 6, 8 are in not B. Again, I could compare the universal roster to the B roster, take out 4, 5, 7, and those are the things that are left. All right, A minus B, my difference of sets. Now I'm just interested in set A, so I don't think about anything except what's inside of set A, and then I subtract anything in B. So I take out what's in B, and all I'm left with is 2. And finally, start with B, subtract A. So I'm only interested in elements in set B, and then I take out anything that is also in set A, and B minus A is what I'm left with, 5, 7. Okay, let's look at the next page. On the next page, we have another Venn diagram with two loops, sets A and B, both inside a universal set. Notice that there are two elements that are in the universal set that are not in either A or B. The universal set includes 1, 2, 3, 4, 5, 6, 7, 8. So all of my natural numbers from 1 to 8 are my universal set. That's what makes up my universal set. Now I need you guys to go through and answer these 8 questions based on this Venn diagram. I want you to pause the video, do your work, and then come back and compare your answers to mine. Okay, I assume you've started us back up because you are done with this page and you're checking your answers. Loop A is everything inside that A circle, so I'm covering up anything not the A circle for set A. Set B, I'm only looking at those 4 elements inside the B loop. A and B, remember this is my intersection. This is my keyword and. I'm only looking at the region that they share. For the keyword or for union, I want anything inside the loop, either A or B or both. So I include everything except these elements that are in the universal set but outside. So my union are all 3 regions. My intersection is just the region they share. Then the second column includes complements and set differences. For the complement, for A complement, I would cover up set A. A complement is anything not in set A. For B complement, I cover up set B, and it includes anything not inside set B. When I'm doing A minus B, I start by looking just at what's inside set A, and then I think, okay, I'm going to subtract anything that's also in B. For B minus A, I go the other way. I start by looking just at what's in set B, and I exclude anything that's also in A. All right, let's look at the next page and see what we have. We're going to start with a review of what we've been working on. Intersection versus union, complement versus set difference. First, we want to think about the symbols for intersection, union. Then we want to think about the keyword for intersection or union. Remember, intersection, it has to be in both, must be in both. Later on, when we're doing 3 sets, to be in the intersection of all 3, it would have to be in all 3. Union can be in either or both. Remember, it's my inclusive or. It can be in either set A or set B or both sets. Then we have complement versus set difference. For example, complement would be a complement. Looks like that apostrophe, that prime, a prime. It means all elements not in A. All elements not A, not in A. Then set difference looks like subtraction, A minus B. A tells me where we start, and then we subtract out, take away anything that's in B. So everything in A, all in A, but not in B. That's my set difference. All right, now we have an example where we're starting with roster form and we need to draw the Venn diagram. I'm given a universal set, set A, and set B. So I have my universal set, I have set A, and I have set B. My universal set lists my natural numbers from 1 to 10. So let's see. Let's start with set A. Set A has a 2. There's not a 2 in B. Set A has a 3. There's not a 3 in B. Set A has a 4. There is a 4 in B, so they share 4. Set A has 5. There is a 5 in B, so they share 5. Set A has 6. There is also a 6 in B, so they share 6. That's all of set A. When we look at set B, we've already done 4, 5, and 6. B also has 7 and 8. Those numbers were not in A. Do we have any elements that are in the universal set that are not listed in the roster form of A or the roster form of B? Well, yeah, because our universal set starts at 1 and goes to 10. So we've got 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 9, and 10 are the 3 elements that are part of the universal set, but not in A or B. Now, to answer these questions, we're going to have to know some intermediate sets. Let's go ahead and number these to make sure that we go in the same order. We're going to go across 1, 2, 3, 4, 5, and 6. We have to know some things. Before we can figure out the intersection of not A with B, we have to know what's in not A. I can look right here and see what's in B, but I have to know that intermediate set. Now on the practice, on the homework, you're going to have to give me intermediate sets. So make sure you get in the habit of doing it now. Before I can find this intersection, before I can get the answer that I'm being asked for, I need to know what is in not A. Well, A includes 2, 3, 4, 5, 6. If I cover those up, these are the 5 elements that are not in A. 1, 7, 8, 9, 10. 1, 7, 8, 9, 10. Now I have to see what that list shares with my B list. I can either look up here or I could go ahead and rewrite it. I don't have to rewrite it, but if you're struggling a little bit, it might be easier to rewrite it. Okay, the question I'm being asked is the intersection, the and, what is in both, not A, and at the same time in B. So I'm looking for elements that are in both lists. Well, I see that 7 is in both lists, and I see that 8 is in both lists. So the intersection of not A with B are the 2 elements 7, 8. All right, let's look at number 2. Number 2 tells me to find the complement of A or B. Well, order of operations for set theory pretty much works like order operations for adding and subtracting, multiplying and dividing. I start with parentheses first. So I need to know that A or B, that union, I need to know A or B before I can take the complement of it. So let's look at A or B. That's my intermediate set. I had to know A prime here for number 1. I have to know A or B here for number 2 before I can answer the question I'm being asked. Well, or is my inclusive or. Anything in loop A or B or both gets included. So it's everything except these 3 elements outside. So it's 2, 3, 4, 5, 6, 7, 8. So A or B, roster form 2, 3, 4, 5, 6, 7, 8. That's not the question I'm being asked. The question I'm being asked is the complement of that. What is not in this list? Well, the things not in this list are these 3 elements that were left out, 1, 9, 10. You have to do the intermediate set first. You have to show me that intermediate set. All right, let's look at number 3. Number 3 has a difference, A minus not B. Well, I can see A pretty clearly. A is right here on my Venn diagram. It's right here as a list. What is my intermediate set that I have to know before I can answer this question? Well, I have to know the complement of B. My intermediate set is not B. Well, anything outside the B loop is not B. So let's look at our Venn diagram. Cover up your B loop. And those 5 elements that are not B are the ones I want to include in my complement of B. So I have 1, 2, 3, 9, 10 as not B. Now, I'm doing A minus this, so I can copy A down if I want, or I can just look back up. A, take away, not B. So I'm starting with the assumption that I have 2, 3, 4, 5, 6. That's what is in A. I need to take away any elements that are in my not B list. Well, 2 is in my not B list, 3 is in my not B list, so I don't include those 2 elements. I'm left with 4, 5, 6. Okay, what about number 4? Order of operations again. What's my intermediate set that I have to figure out? Well, it's what is inside the parentheses. So my intermediate set that I have to do first is the intersection of A with B, A and B. I can look at my Venn diagram and see very easily my intersection. What they share are those 3 elements in that one region right there, 4, 5, 6. The intersection of A and B is 4, 5, 6. The question I'm being asked is to find the complement of that intersection. So what is not in this list? Well, everything that's in the universal set except 4, 5, 6 is not in that list. That leaves me with 1, 2, 3. There's my 4, 5, 6, 7, 8, 9, and 10. All right, number 5. I need the union of not A or not B. The union of not A or not B. Well, to get that union, I first have to know not A, and I have to know not B. Now, we've already found those, so I'm just going to go ahead and write them down here. We found not A up here for number 1. And we see that outside of A, we have 1, 7, 8, 9, 10. And then we found not B here for number 3. 1, 2, 3, 9, 10. Oops, not B. 1, 2, 3, 9, 10. What I'm asked for is the union of those 2. So if it is in either list, I get to include it. So we're going to do alphabetical. Order from least to greatest. We get 1. We only write it down once, even though it's in both lists. Then we have 2 and 3. We don't have 4, 5, 6. I don't see them in either list, but we have 7, 8, 9, 10. My final question here, number 6, is the complement of A minus B. So before we can take the complement, we have to find A minus B. That's my intermediate set. To find A minus B, I start with loop A, I start with set A, and then I take out anything that's also in B. So A minus B, there's A, minus B is just 2, 3. The complement of A minus B is everything else, everything in the universal set, 1 through 10, that's not in this difference. So I list all of the other values. There's my 2, 3, so 4, 5, 6, 7, 8, 9, 10. All right. That was some really good practice. We have one more page, one last concept that we're going to talk about in this section. The Cartesian product, not to be confused with the cardinal number. The Cartesian product of 2 sets is symbolized by this. It looks like multiplication, but it kind of is, but not exactly. We would say A cross B. When we see that symbol for Cartesian product, we would say A cross B. It's the set of all possible ordered pairs in the form of AB, where little a is an element of set A and little b is an element of set B. We're going to do 2 sets of these so that you can see how they work. Determine the cross product. Identify the cardinal number of the cross product. Well, let's practice our cardinal numbers. The cardinal number of set A is how many elements there are in A. So there are 3. And the cardinal number of set B would be 2 because I've got 2 elements in B. Now we're going to do A cross B, and then we're going to come back and do B cross A. Let's do A cross B first. So if I do A cross B, I'm doing ordered pairs where each element in A gets paired with each element in B. A comes first. So I open my fancy braces to show that I'm listing elements. And then inside that I have ordered pairs. So elements of A are my numbers 1, 2, 3. We're going to start with 1. We'll pair it with A. And then we also need to pair 1 with B. So there are 2 ordered pairs. Then I move over to element 2 and I pair it with A, and then I pair 2 with B. And then I move to element 3, pair it with A, and 3 paired with B, so that I have linked in ordered pairs each element of A with each element of B. Well, how many ordered pairs do I have? What is my cardinal number of A cross B? 1, 2, 3, 4, 5, 6. So N of A cross B is 6. Now let's do B cross A. We're using the same 2 sets, A, B, but we're going in the opposite order. So we start with the elements of set B first. So instead of starting with 1, I start with A, and I pair it with 1, then 2, then 3. So I have A1, A2, and A3. Then I move to B and pair it with each. So B1, B2, and B3. So each element of set A has been paired with each element of set B. And I have 1, 2, 3, 4, 5, 6 ordered pairs in that Cartesian product. So order matters because 1A is not the same ordered pair as A1. Order matters. It matters whether I do B cross A or A cross B. But notice that they each have the same number of ordered pairs. They each have the same cardinal number. Where do you think that cardinal number came from? Well, hopefully you noticed that I took the cardinal number of set A and the cardinal number of set B to get there. Let's do A cross or C cross D and D cross C. So for C cross D, I'm going to start with A, and then I need to pair it with each element in D, which gives me 4 ordered pairs. The cardinal number of C cross D is 4. What do you think is going to be the cardinal number of D cross C? Hopefully you said 4 as well, but the ordered pairs are going to look different. I didn't get that color I wanted. I have, this time we're going to start with D. So we have 1A, we have 2A, we have 3A, and we have 4A as my ordered pair. So the number of D cross C is also 4. We didn't give the cardinal numbers of C and D. The cardinal number of C is 1, and the cardinal number of D is 4. And 1 times 4 is 4, just like 2 times 3 is 6. Can we say that A cross B is equal to B cross A? Well, no, because these sets of ordered pairs are not the same. No, order matters. Which set you start with matters. If n of A equals 7, so the cardinal number of A equals 7, and the cardinal number of B equals 10, then what is the cardinal number of A cross B? Well, it's going to be 70, because 7 times 10 is 70. All right. Now we have a challenge problem down here. It just helps us to form a general conclusion. We're going to use a little bit of inductive reasoning again, starting with a specific example and forming a general conclusion. In fact, we've got the universal set and just set A, because this is our empty set. So let's do our very small Venn diagram where we have universal set, we have set A, and within the universal set we have the numbers 1, 2, 3, 4, 5. 1, 2, 3 are in A, which means 4, 5 are out here in the universal set. Let's answer some questions about that. A intersects the universal set. What do A and the universal set have in common? Well, they share 1, 2, 3. A or the universal set. If it's in A or in the universal set, we get to include it. Well, the universal set is everything. So that is 1, 2, 3, 4, 5. Then we have the intersection of A and the empty set. What elements does the empty set include? None. So that's going to have to be the empty set. The only thing they share is the empty set. What about A or the empty set? Well, if it's in A or in the empty set, we get to count it. So we can count anything that's in A. 1, 2, 3. Now I want you to notice some things. When we did A intersect U, A intersects the universal set, we got 1, 2, 3. 1, 2, 3 is the same thing as set A. When we did A or the universal set, we got 1 through 5, which is my universal set. Then A intersect the empty set is just the empty set, the null set. A or A union with the empty set gave us A again. So in general, if we have any set A intersecting with the universal set, that's the same thing as that set A. If we have any set A or the union with the universal set includes everything, so that's going to be the universal set. If we're looking for the intersection of any set with the null set, it is the null set. And if we're looking at the union of any set with the null set, well, it's going to be whatever that set is. So we took a specific example and formed a general conclusion. When we go from a specific example to a general conclusion, this is an example of inductive reasoning again. Remember, we can't prove inductive reasoning because it would only take one counterexample to show it false.